So in this video, we're going to introduce the concepts of power and energy from a circuit analysis perspective. And what I mean by that is hopefully it's a bit of a review for you to say that power is nothing more than the rate of change of energy, namely how quickly energy is actually being supplied or how quickly it's being absorbed. And I know a lot of you might be familiar with different terminology for that, like instead of absorbed, actually consumed, or instead of supplied, actually produced. So hopefully you'll be flexible a bit with me. Absorbed and supplied is the terminology that the book uses, and I'll try to be consistent with that, but note sometimes I may vary from that. So you can compute the power associated with a two-terminal element, and we'll talk about the sign convention of determining whether it's absorbed or supplied in a minute. It's simply taking the product of current times voltage, so P equals I times V here, and that's always going to be a valid formula. If you think about the SI units of I and V, I being in amperes, which is coulombs per second, V being in volts, which is joules per coulomb, if you perform dimensional analysis and find the SI units of power, what you would see is that it's 1 joule per second, and that is the definition of 1 watt of power. So in terms of the sign conventions of power, if you're going to employ that P equals IV relationship, basically the idea is as long as when you use that formula, current enters the positive terminal of whatever voltage is associated with pushing or driving that current and exits the negative terminal, then it satisfies the passive sign convention. So if you look here at this diagram on the right, the current is entering the positive terminal and it's exiting the negative. And whenever you have that case, you can just take whatever the number is for V and I, multiply them together. And if you get a positive number, what that means is that that component is actually absorbing power. Versus if the number were to be negative, that means that the component is actually supplying power. And if you think about it, it kind of makes sense because if this were to be a battery, remember that conventional current is positive charge. So it's going to be pushed out of the positive and go to the negative. So if it were to be supplying power, it would work. The current would be going the other way. The book overcomplicates this a bit. It overcomplicates it a lot. Basically, if you have a current and voltage pair that are not following passive sign convention, the only thing you need to do is add in a negative, and then you still basically in your formula, so just P equals minus IV if you're not following passive sign convention. And you can use the same interpretation for positive and negative sign of the result as we have here. If it's positive, it's absorbing. If it's negative, it's supplying. So energy, of course, we know that if we take that differential relationship between power and energy in the prior slide, and we separate the terms and we integrate, then we can compute the energy at any point in time by simply integrating the power function and adding on that initial condition. And power from an electrical circuit point of view is going to be a quantity that we deal with much more. However, there are some important applications of energy, such as quantifying the total life of a battery or estimating maybe your electricity bill at home. And on that later note, one thing that all of you are probably familiar with is even though the SI unit of energy is joule, when we're talking about energy from an electrical perspective, it's common to see kind of products of power and time utilized as an energy unit as well, something like the watt hour or more commonly the kilowatt hour in actual household industrial examples. So example problem 1 here, compute the power absorbed in each of the scenarios depicted below rather. So it's just going to be P equals IV as long as it follows the passive sign convention, which means that this arrow is pointing in on the positive. So arrow is pointing in on the positive, arrow is pointing in on the positive, arrow is pointing in on the positive. You notice when I did that, I didn't worry about whether or not these numbers were negative. We'll let the math take care of itself in that case. And let's actually see how that looks here. Here we have the arrow going into the positive, passive sign convention is followed. I times V is just going to be 6, and that is in SI units of watts. Here, same thing, passive sign convention is followed. It just so happens the I and V numbers are negative. So when you do that multiplication, you get 6 watts. And you might ask yourself, well, like how? It seems like it's the same number. What's really going on? Well, remember, whenever you have a voltage with plus on the bottom and minus on the top, you can swap the polarity as long as you change the sign. So plus on the bottom, minus on the top, minus 2 volts is the same as plus on the top, minus on the bottom, positive 2 volts. In a similar fashion, right, this current, it would pass through and it would actually leave the top terminal, but it's negative 3 amps. You can always change the direction of the arrow by just swapping the sign of the current. So minus 3 amps going to the right is same as 3 amps going to the left. So these are actually the same thing, so not surprising that it is 6 watts. In this last example, sign convention is actually followed. You have that negative 5 amp current going into the positive terminal. So I can just multiply the two numbers together. 4 times 5 is minus 20. That is in watts. And what is the minus sign telling me there? Well, all of these two quantities, right, they were positive. And since we followed the passive sign convention, that means these top two components were actually absorbing power. However, if you notice here, we have a negative when we followed the passive sign convention. That means that this component is actually producing power. And that makes sense, again, because if you think about minus 5 amps going to the right, that's same as 5 amps going to the left. And if it were to be going to the left, that would be current that's actually leaving the positive terminal of the source, which is kind of how a battery works when you think about the conventional current theory, as we mentioned in the previous slide. So let's do this particular example. We have a battery-powered smoke detector. It has an average power consumption of 0.5 milliwatts and runs off a 9-volt battery with a capacity of 500 milliamp hours. So when you talk about capacities of batteries, there's lots of different ways to see them. It's very uncommon to see them measured in joules. Sometimes you see them measured in units of charge, or since charge is simply the rate of, current is simply the rate of flow of charge, you can also see them specified in terms of milliamp hours. So we're seeing how long we need to change a battery here. Really, this is just a problem in dimensional analysis. You know that the average power consumption is 0.5 milliwatts, or 0.5 joules per second of energy is being consumed. You know that the terminal voltage is 9 volts, and you know that the total energy capacity is 500 milliamp hours. So the question becomes, given this average power consumption and this terminal voltage, can you find the actual average current draw? Because if you think about the units that you were given for energy here, they're kind of in units of so much current per or for an hour, right? Not per is more like division, but this can produce 500 milliamps for an hour, or it could produce 250 milliamps for 2 hours, and so on. So the question is, what is the average current that's actually being drawn by this load? And we can just use Ohm's law here if we want, right? Or sorry, not Ohm's law, but the formal definition of the power formula, P equals IV. If we solve that for I here, as long as P is average and V is constant, I will also be average. And the power value divided by the voltage value is just going to be 0.05 repeating milliamps. So that's how much flow of charge is coming out. We know that in total we have this capacity of charge inside the battery. 500 milliamp hours divided by 0.05 repeating milliamps is just going to be 9,000 hours, or 375 days, and that passes a little bit of a sanity check because you're generally recommended to change your smoke detector batteries every year.